Greetings. Let's talk about implicit differentiation, which is a process for differentiating when you don't have an explicit formula for a thing that you're working with. The point of this is that it builds on the chain rule to let you be able to take derivatives when you don't know explicit functions. So, for example, I'm going to transcribe from the book and use a book problem because I think it's a great source of problems, and you should do book problems too. So let's take a look at the function xy plus x squared y squared equals 6. Okay. So we've got this equation right here, and it's pretty clear that if you choose a value of x, you get some values of y, right? If you choose an x, you get some values of y. Like if I put like x was 1, you'd have like y plus y squared equals 6, a quadratic, and you get 2 values, okay? And likewise, if I like start doing some things, like if I put in x is 0, if x is 0, then we'd have 0 equals 6, which is nonsense. So there is no y if x is 0. So there's some set of points that satisfy this constraint that emit some curve in space. And this is not the curve for this particular example, but imagine that it is. And so what we can do is we can still compute slopes of tangent lines even when we just have this thing by implicit differentiation, which is essentially the chain rule. So the first thing we're going to do is we're going to be like, let's choose a variable to be your independent variable. Commonly, x is a good one to choose to be your independent variable, or time, x or time. And then we're going to note, this is a really important note right here, we're going to pay attention to which symbols are actually functions of the other things. So y is a function of x, because if we fix x's, then we get some y's, right? So y is dependent on x. And this right here is going to be key to taking the derivative of this thing correctly. So what I'm going to do is I'm going to take the derivative of both sides of this expression, because if two things are equal, then their rates of change are always equal. Like if we're driving on the highway and you're driving right beside me and our positions always match forever, then we have to be going the same speed as each other, right? So take the derivative of both sides, and they'll still be equal to each other in terms of actual rates. So the derivative of the left-hand side here, I'm going to take the derivative of this. Now check this out. This thing right here, this xy, I'm going to have to bust out the product rule on that because it's x times y. Now let's see how it goes. So let's go. The derivative of the first is 1 times the second plus the first times the derivative of the second, y, which is y prime, dy dx. I'm going to go ahead and erase that. 1 times plus, let's do this one here. So we're going to have to product rule that thing also. So the derivative of the first is 2x times the second plus x squared times the derivative of the second, which is 2y times dy dx. How it depends on that because of the chain rule. We don't know this thing, but it exists. Right? So as a reminder, we're trying to figure out what this rate of change is, and we don't know it. And the chain rule says that you take derivatives of things. So you've got some outer function, something squared. You've got some inner function, y. We just don't know what its derivative, so we still have to have a placeholder for it. Okay? What's the derivative of 6? 0. It never changes. Okay. And so now we're going to solve for dy dx, because that's the thing I want. I want to get what y prime is, essentially. So I'm going to put everything without a dy dx on the other side. I'm going to leave everything with a dy dx on this side. So how about I go x plus x squared times 2y. I'm going to omit the dot times dy dx. I went ahead and factored out the dy dx in one step there. I feel like That's appropriate. And then everything else without a dy dx is going to go to the other side. So here's a term without it. Here's a term without it. So how about I go minus y plus 2x y squared. And then finally, dy dx is equal to minus y plus 2x y squared over x plus x squared 2y. And we have our rate, we have our derivative. So there's this curve, and we can compute slopes to tangent lines to that curve by this method right here. So we could say evaluate that to compute the slope of the tangent line at the point, let me make sure I choose one that's actually on the curve, 2, 1. First, let's check and make sure that this actually is on the curve. 2, 1, I'm going to feed that into this expression right here. So I'm going to have 2 times 1 is 2. Plus 4 times 1 is 4. 2 plus 4 is 6. Boom, check. Checks out. It's actually on the curve. That's awesome. I love it when that happens. Right, if I'd been given like a 2 here, it'd just be nonsense. We can still compute this value here, but it's just not actually the slope of a tangent line. And all we have to do to get the slope of this tangent line is take this expression right here and plug it into this expression right here. Right? So that's dy dx evaluated at 2, 1, which is equal to minus 1 plus 2 times 2. I'm going to omit multiplication by 1 over 2 plus 4 times 2 times 1 is 5 over 10 is a half. So the slope of the tangent line is a half. So whatever the curve is doing, we don't have a plot of the curve. I could teach you about how to plot these curves using implicit plotting. We're not going to do that. So the slope to the curve there is a half. And implicit differentiation revealed that to us. So whenever you take derivatives of y's, make sure you chain out the derivative with respect to the next thing in the chain, the independent variable, like that, and you'll be set. So thanks for watching, and I hope you have a nice one.